All right, hey, were you absent from class the week of November 30th? This was a class kick activity that we did. So what you see here, these are answers to the problem on slide 2. And so just take a look at these answers. Big thing to note here is that there's two different motions in this story about the dog. The dog's moving at a constant rate of 5 meters per second for 8 seconds. That's represented by all the yellow pieces here. And then the dog uniformly increases velocity. That means they're accelerating over the course of 5 seconds up to 10 meters per second. So accelerating from 5 meters per second to 10 meters per second over the course of 5 seconds, 8 to 13. Okay. So take a look at these answers. And if I scroll a little bit, I kind of ran out of table space here, so I just extended beyond it. So you see the acceleration of 1 meter per second per second. So at 8 seconds, it starts increasing by 1 each second. Okay. All right, so you can go back to that if you need. All right. We go to the next slide. This is a new problem. So pause the video and read this problem. All right, so there are two questions being asked. What does the initial slope of Scott's line need to be on a velocity time graph? And the same question for Aaron. The answers are here, A and B. So the reason is because Scott is traveling with an acceleration of 4 meters per second for 6 seconds. Well, on a velocity time graph, the slope is the acceleration. So if we're given the acceleration in reverse, you know that the slope is the same number. So the slope or the acceleration is 4 meters per second. That means that the slope is 4. And this acceleration is 3. That means that the slope is 3. Okay. All right, the next slide. This is the same problem. And note that it gives that answer that I just said right here. And it wants you to draw a velocity time graph for Aaron and a velocity time graph for Scott. And note the colors that it asks. So before you do that, I want you to note something in this problem. First of all, Scott leaves first. They both leave from rest. And then 2 seconds later, Aaron starts. So they're not starting at the same place. The other thing I want you to notice is that both people's motion have an accelerated motion part, so acceleration, and then they have a constant velocity piece. Okay, acceleration, constant velocity. So Aaron's motion has 2 different motions, Scott has 2 different motions. Go ahead, pause the video, graph this, and see if you're right. All right, so these are the answers. Now, I knew that that Scott, the red line, would make it up to 24 meters per second. And I knew that the purple line would make it up to a velocity of 30. How did I know that? I knew that because I knew I was going 4 meters per second for 6 seconds. So if I had a velocity time chart here, time 0, 1, 2, 3, and so on. I start from rest. Well, 1 second later, I'm going 4 meters per second. Another second, I'm going 8, and I'm going 12. So this becomes multiplication or repeated addition. So 6 times 4 is 24. The seconds cancel. And you're left with meters per second. So that tells me that if I accelerate at 4 meters per second for 6 seconds, and I start from rest, I will make it to a speed of 24 meters per second. So that means for Aaron right here, he's going to make it to a velocity, I should say, of 30 meters per second. 3 times 10. All right, so that's how I knew I got to 24, and this got to 30. We have our accelerated piece, where the velocity's, in this case, increasing, and we have our constant motion piece on each. So there's questions below this. The question is, who do you think is going to travel further? Do you think it will be Scott, the red one, or do you think it will be Aaron? So pause the video and answer that, and answer why. This is a prediction. We don't yet know enough physics to answer this, so we're making a prediction. Okay, so if you predicted that Scott travels farther during the 16 seconds, you are correct. If you are incorrect, don't worry. Sometimes making incorrect predictions helps us. We're going to learn why in a little bit. All right, so we have a new problem here. We have Mr. Schutz. He's circled in yellow right here. Mr. Schutz rides his bike at 5 meters per second for 4 seconds. So answer this to yourself. How would you describe Mr. Schutz's motion? Is he moving at a constant pace? Is he speeding up, or is he slowing down? Answer that. If you said that he's moving at a constant pace, you are correct. He's moving at 5 meters per second for 4 seconds. Okay? So what I want you to do right now is I want you to graph the velocity time graph. I want you to create a position. I have a little typo here, but your position time data table. Note that it's position time. It's not velocity time. And I want you to create your position time graph. All right, so go ahead and pause the video and make sure you try this out. Okay, so these are the answers. Ooh, I want to erase something because it's not relevant yet. So these are the answers. Mr. Schutz rides his bike at 5 meters per second for 4 seconds. So he's going, this is 5 on the velocity. 5, 5, 5, 5, 5. My position time graph, well, if I start from rest, which he does, 1 second later, I've traveled 5 meters. Why? Because for this 5 meters per second means that for every 1 second, I travel, or Mr. Schutz travels 5 meters. Written another way, you see right here, 5 meters over 1 second. Every 1 second, you travel 5 meters. That means that after 1 second, you've gone 5, you're at position 5. After another second, you're at position 10, and then position 15, and then position 20. I can plot this data on this position time graph, and it would look like this. So there's questions below. Answer those. Pause the video. All right, so how does the slope of a position time graph relate to the velocity time graph? Well, the slope of the position time graph is the velocity. Okay. How far did Mr. Schutz travel during the 4 seconds? He traveled 20 meters. How did you know that from the data table? Because the last row made it to 20 meters. How did you know it from the graph? Well, you just read the graph. The highest value on the y-axis was 20 meters, and it started from rest, or 0, okay? So finding the position or the displacement is easy if you have a position time data table or a position time graph, because you can just straight up read the value that's given to you. The question though is, how could I figure out how far Mr. Schutz traveled if I could only look at the velocity time graph? That is the question from earlier when I asked who traveled farther, Scott or Aaron. And this is the trick. If you take the shape that's between the function, the purple function, and the time axis, and you find the area of that shape, that will be the displacement. So let's try that out and see if it works. All right, so this is a rectangle. The area of the rectangle well, let me try this again. The area of a rectangle equals length times width. Okay. So what is our length here? Well, if we call this direction length, it is 4 seconds. What is the width here? It's 5. Goes from 0 to 5, so 5 meters per second. So what's 4 seconds times 5 meters per second? The seconds are going to cancel, and you're going to get an area of 20 meters. Well, hey, wait a minute. 20 meters. 20 meters. 20 meters. So the area of the shape between the function and the time axis gives us the displacement. That's pretty snazzy. All right, so here's what you're going to do. You are going to watch this 7-minute video that reinforces that area idea that I just talked about. After you watch that 7-minute video, you're going to come back to slide 9 and you're going to try this. Okay. And then you're going to go to slide 10. Find the area of this new shape or new object. Slide 11. Notice that the areas can be positive and the areas can be negative. Now this shape, this is not a this is not a rectangle, this is a triangle. So you need the area of a triangle. If you don't remember that, you can just Google it. And then you get to the next slide, and this is an irregular shape. It's not a normal shape. Now, math teachers probably know what the formula is for this particular irregular shape. I don't know it. So you know what? I'm going to rely on the shapes I do know. I know I have a triangle. And I know I have a rectangle. Those are very ugly triangles and rectangles. But if I found the area of this triangle and I found the area of this rectangle and I combined them, I would know the total area between the function and the time axis. All right, so watch the video on slide 8 and then try out slide 9 through 13. That is your asynchronous assignment.